Yo Minasan. Today we will learn about lecture 3 summary. So in this we are learning about resistance and resistivity. So let's get started. So first of all, we will learn basically about uh, R equals to rho L by A. Some examples in a cuboid of length height h, length L and breadth B. If we name this phase as 1 and this 2, if current is passing through 1 and 2, we will say that R12 will be rho L by rho rho L by H into B, which is the area EH. If we consider above the other two phases, 3 and 4, if it is going like this, we'll say R 3 4 would be rho. Here H is the length through which the current will be passing through, so it would be rho H by BL. That's it. Then next one is, now we'll see about a hollow cylinder of thickness. In this, this is R1 and inner radius is R2. So as it is uniform and each of the each point in this resistor is same, so if we are to pass the current through this conductor, we'll we'll just have to subtract this part as it is uniform. So R equals to rho, here length through which it passes is L, rho L by area here is pi R1 square minus pi R2 square. So pi R1 square minus R2 square. This is our answer. But what if it is not uniform? Then we'd have to uh, we'll consider an example, which is example 3. In this we have a sphere. In this it is a hollow sphere, so only from uh, its actual radius is R1, actual radius is R2, and the hollow space radius is R1. The resistivity is rho. If we see this, what is varying here is our surface area increases as we go outwards the shape. So R is basically, we'd have to integrate all these areas. So if you consider uh, one such part, which is x distance away, here we are considering, yeah, x distance away, and its thickness to be dx. So now basically its surface area of a sphere is 4 pi r square. So we'll just say here, for a small resistance it would be dr equals to rho dx, as it is going through dx space, divided by 4 pi x square. Now, if we integrate this through from R1 to R2, we should be able to get our desired result. Now, R is equal to rho by 4 pi, we take it outside, x square. 1 by x square integration would be minus 1 by x. Yeah, minus 1 by x. So R1 to R2. Basically, it is R1, R2. Let's just simplify. 1 by R1 minus 1 by R2 by 4 pi. It is rho by 4 pi R1 R2 by R1 minus R2. That's our answer. Now we go to next up. We have another example where resistivity, not resistivity, but rather the whole area is again changing. This one, a conic section, frustum, I guess. And this one, its length is L, and here its radius is R1. This is R1. This is R2. Now, if current passes through this type of conductor, what would be its resistance? Here, uh, just A is varying, so we just have to integrate. Take one small piece here. Now, if we would have to write its R in terms of, we are considering its radius as R, so we have to express that R in terms of the known quantities R1 and R2 and other known quantities like L. So by here, this little space here, we are considering it the triangle made by, from here to here, if we join the line, triangle is made. So by similar triangle rule, first we'll write the, here if we consider R, then this little space here would be R minus R1. This would be, if this is X, then the, yeah, that is X. So, and the thickness is dx, and the thickness is dx. So R minus R1, R2 minus R1. By similar triangle CPCT, I guess, that is R minus R1 by X equals to R2 minus R1 by L. So R, we can write it as R1 plus X times X by L times R2 minus R1. Now we just put this in the formula. First of all, we know that R equals to dr equals to rho. Here the space which through which it is moving is dx upon uh, the area would be 4 pi r square. Not 4 pi r square, it is pi r square. Here r is this r, so we just take out, while integrating, we integrate it from, we are integrating in terms of x, so we go from 0 to L. So r is equals to rho by pi 1 by r square integration, but r we have to write in terms of these, so r1 plus x by L r2 minus r1. We have to integrate it from 0 to L. As this is a complicated Yet we can simplify it. We consider this whole thing as t r1 plus, so let this be t. If we differentiate, we get uh, r2 minus r1 by 2 dx equals to dt. But here we don't have that. So we'll try to bring r2 minus r1 by L. We'll just multiply and divide. So that would be L by r2 minus r1. And here it would be dt by t square. Now the integration is easy, so that would be rho L by r2 minus r1. This is minus 1 by t. This is 0 to L. The limits are still same, but we won't put that right now. We'd have to again consider the older limits, that is the older value for t which we had for minus 1 by r2 minus, not r2, that's r1 plus x by L, r2 minus r1. This is 0 to L. First of all, 0 part, that would be rho L by pi r2 minus r1. 0 part would be 1 by r1 minus 1 by, if we put L, that would be r1 will get cancelled out, r2, and if we put here, this would be r2 minus r1 by r1 r2. So at last we have rho L by pi 1 by r1 r2. That's our final answer. Next up, we have, this was when area is varying. What if, what if, what if the whole resistivity started varying? Just consider cylindrical wire. Here, A is the same, length is the same, L is the length, A is the area, I guess. Yes, A is the area, but rho changes. It changes by rho equals to rho equals to rho naught e power minus x by L. So we just a minute. Here, as the value of rho is changing with length, we'll just consider one small cut. Here its thickness is dx, and yeah, from here to here its length is x. So, and it's still having area A. Now, for such small segment, dr equals to rho, which is, we'll substitute it later, dx by A. Now, integrate 1 by rho naught by A e power minus x by L का differentiation dx, which is r, limits are from 0 to L, rho naught by A, we'll first integrate minus x by L 0 to L, we divide by what we had, we divide, so minus L say divide, then we have rho by L. So minus L e power, if we put 0, first of all, it would be e power minus 1 minus e power 0, which is 1. If we want, we can take the minus inside, 1 minus 1 by e. We can simplify further, but that's all. Then we later have Ohm's law. Ohm's law is simply V equals to IR. Here, main point we have to remember is that if we move along the current, IR potential IR will increase, and if we go opposite to the flow of current, so if we say current is going here, then if we go from here to here, V will decrease, which is I into R. It will decrease. But if we go in the opposite direction of the current, which is lower to higher potential, obviously it will increase. Then we have some silly questions, which is uh, we take a fairly difficult one. Let it be 3 ohms. This one is V1 equals to 10 volts, V2 equals to watt, and current passing through is I equals to 2 ampere. So here we know that V equals to IR, so we need V2. So this is higher to lower, so this one is higher, this is lower. V2 minus 10, we already know resistance into this is 6, so V2 is equal to 16. Nah, man, I think I took the direction wrong. Yeah, direction of current is that way, so it is 10 minus V2 equals to I into R. 2 into 3 is 6, so V2 equals to 4 volts. Next up, we have dependency of R on L and A. So basically, this is about stretching, and yeah, this is about stretching of wire. What if its area has increased? But mostly it is about stretching of wire. So we are considering uh, the volume conservation, because if we stretch a wire, its area will decrease and length will increase, but they will maintain the volume which they have. So we volume is A into L. So if we increase this, this should decrease, and if we increase A, L should decrease. So with keeping that in mind, we'll say, what if L is increased? If L is increased, we'll say we have another formula, which is R's dependency. R equals to, we know, rho L by A. If we express this in terms of L, it would be L square by V. And we know that V is not getting changed, so we'll consider it as K. So R is directly proportional to L square. R is proportional to L square, and R equals to rho by V L square. Now, now let's take an example. So we are given that there is a 30% increase in length. Now we have to find the change in its resistance, or we just have to find the new resistance. And we also need to find the fractional change and also the percentage change. So first of all, 30% means 0.3. Yeah, yeah, 0.3. So L is the original length and increased means 0.3 L. So 1.3 L increase. So this is the latest one, L dash. R dash would be rho. We'll just consider that we know that volume is conserved. So rho by V is constant. So K into L square. So K into 1.3 L square, L whole square. 1.3, it's 169, right? It's 3 3 9, 6, 169. 1.69 KL square. KL square is R, so 1.69 R. The new rate resistance is 1.69 R. So fractional change would be final minus initial. Uh, Final minus initial by initial. That's fractional change. So that would be 1.69 minus 1 times R divided by R. R cancel. 0.69 is the fractional change, and if we needed percentage change, that would be 0.69 by 0.69 is 69 by 100 into 100%. 100 cancel. 69% is our answer. Now if percentage change is very small, negligible, or like very small, then we'd say that percentage change would be delta R by R equals to 2 times delta, not delta, dl by L. Yeah, dl by L. This is our fractional change. If it is very small, ER by R into 100%. This is percentage change, dl by L. Whatever the change we are given, we should just put it here. Then we'll get a percentage change in dr into 100. Nah, it's fine. 100%. Then we have dependency of R on temperature. Here, R equals to R naught into e power alpha delta t. It is the same as earlier we had seen for the first that temperature change with temperature length would change, area would change, or the volume would change. In the same way, resistance also changes with the alpha and delta t. But if alpha delta t is very small, then it would be with binomial expansion. It would be alpha delta 1 plus alpha delta t. Now, later, if we say final minus initial divided by r delta r by r naught is just alpha delta t. This is fractional change, and if we multiply this by with hundreds, we'd get percentage change. Next up, we have one of the example. Example 1 would be if r naught is given 10 ohms and alpha is given 2 into 10 power minus 4 per centigrade, what would be resistance at 15 degrees Celsius. So R is equal to, first of all, we have to check for alpha delta T. Here T minus 0, so 2 into 10 power minus 4 into 15, so 3 into 10 power minus 3. R is equal to R naught 10, 1 plus 0.003, so 10.003. That's our new resistance. Yes, that's our new resistance. But what if it is not? What if alpha delta T is not small? Then we'd say alpha equals to 0.01 per degree Celsius. Then R naught is 10 ohms. Then alpha delta T at 100 degrees Celsius, alpha is 1 by 100 into temperature changes 100, then 1. We won't consider this. We won't consider the approximated formula. We consider this. This is R naught 10 into 2.7 power 1. So that would be 27 ohms. R is 27 ohms. Thank you very much.